Okay, so I was asked to present today on astrophysics data management. I've slightly spruced up the title because that sounded so dry. I thought you might all fall asleep. So I work at the International Center for Radio Astronomy Research, which is part of Curtin and UWA. We have a joint research center working on radio astronomy. And one of the big projects that I've worked on in my time here, when I moved here in 2011, so 10 years, is GLEAM, which if you watch the talk, you'll eventually get to find out what GLEAM stands for. And I thought I'd talk you through kind of what we do in radio astronomy, the kinds of things where data is important, and the kinds of computational techniques that we use, really all the way from observing all the way down to reaching out to the public. All right. So fundamentally, what are we doing? Now, astronomy, of course, is just the study of absolutely everything in the universe. Radio astronomy specifically refers to understanding radio waves from the cosmos. Radio tells you about high energy astrophysics, so where you have lots of electrons, lots of high magnetic fields, cosmic explosions, anything like that. All of this stuff is very, very high energy, and kind of as a result, it's invisible to the human eye. It's not something that peaks in the visible spectrum. So this little object, try the air mouse. Boom. Yeah, there we go. So this object here is a radio galaxy. So you can see this sort of dust lane here. This is a normal galaxy that would be visible to the naked eye or with a pair of really good binoculars. But you can see there's this emission coming out here, and that's only visible in radio. And that is telling you about a central supermassive black hole in this galaxy that you'd have absolutely no idea was there if you couldn't see in the radio. So fundamentally, we're trying to make these images to explore our high energy cosmos. We're using radio telescopes, and nowadays, all that data goes straight into large supercomputers, which people like me program. So here's me, I get the data, and then eventually I give the TED talk. That's a very simplified kind of academic pipeline. Okay, so this is the telescope that I've been working on for the last 10 years. It looks nothing like the clip art that I used. This weird little array of spider-like dipoles is called the Murchison Wide Field Array, and it is located up about 3 hours drive east of Geraldton in the Murchison region. And you can see that there are multiple components to this array, and that's because we combine the signals in order to build a much larger radio telescope. These, what they're called tiles, stretch out across about 3 kilometers. Actually, it's been upgraded to 5 kilometers of the desert, and you could never build a 5-kilometer large, size telescope. So instead, we can stitch things together by using lots of small telescopes, and that's a technique called interferometry. It observes at low frequencies, and so the reason that we have it up in an inaccessible region is because all of us are generating an enormous amount of radio frequency interference. So we need to keep the telescope on a quiet site so that Wi-Fi and mobile phones and FM radio don't disrupt the signals. So here is a sort of demo of what our signal chain looks like. So, there we go. The tile, an individual tile is shown here, and basically electromagnetic waves are coming in, exciting these antennas. That's being fed into what's called a beamformer. That allows us to point this, even though it doesn't look like it can be pointed, it can be electronically steered. We convert that analog agitation of the amplifiers into a digital signal using receivers. And from there, basically, it's all digital data that we are moving around. And this line here, this sort of long line, actually extends all the way from the middle of the Murchison, several hundred kilometers away. It's a fiber line all the way down to Perth. So the computation is all done here in Perth, mostly at the Pawsey Supercomputing Center. And we have this long-term archive, which we've been accumulating the raw data for about 8 years now. And of course, then we have to serve that out. So we have a portal, which then sends it to astronomers around the world. And just to kind of put the data rates in perspective here, whenever the telescope is on, it's recording about a Blu-ray per second. So all of those special features, all of that high definition video, all of that compressed into a single second, and then another second, and then another second, and another second. So all of this has to be very fast. And for that reason, we use GPUs quite extensively because they're very fast and power efficient. So when that is all sent down here, we have this storage, which is about 1 million Blu-rays. And yeah, people like me are like, please don't delete the data. And people like the guys who maintain the storage are like, please delete some data. So there's kind of this constant tension between wanting to have large storage and it being really, really inconvenient. Most of this is in tape, so it's very power efficient. But we do have to have some spinning disks so we can actually access the data. All right. So people like me, I'm a research fellow. We program these wonderful supercomputers at the Pawsey Supercomputing Center to actually do the work, right? Like, I don't sit there with a slide rule. That's astronomers from 60 years ago. I write a bit of code and test it extensively. Then I expand that out to work on more data, run it again, until I've got like something that's production worthy. And then I will say, okay, that's it, go for it. I'll queue up 1,000 jobs and process an enormous amount of data. So here's just the feeling of what that's like is summarized nicely in this XKCD comic, where you think, okay, I'm going to make this all faster, but actually it ends up taking quite a lot of development time, and then you've got to maintain the damn thing. Anyway, tools like GitHub and Overleaf are really great for collaboratively developing this kind of thing. So yeah, when I first moved here, what could I program in? Tiny bit of Python, quite a lot of Bash, bit of Fortran, and now almost exclusively I use Python. And if we need to do any heavy lifting, we just use NumPy, which is all C in the back end. All right, so what kinds of data processing are we doing? Well, there should be. There we go. Okay, so I'm actually going to use this image here as a kind of example of like what is actually happening. So imagine that this is the sky, right? I've got this lovely full color image. It's apparently of me, but I thought this would be a little bit more, you'd understand what you were looking at a bit more than if I showed you random astrophysical objects. So here's me, and now we're going to sample it with this, with this single dish telescope. So here, the single dish telescope, if it were infinitely large, would have an infinitely small resolution, and I could pick up all of these individual pixels. It would take a long time. Now, if we use an interferometer, which, as I say, allows you to build a big telescope, then the distance between the different elements of the interferometer sample different angular scales on the sky. So that means if I put my telescopes really far apart, I see really, really small things on the sky. And if I put them close together, I see big things on the sky. You can't actually retain the total power. So anyone who's done a bit of math will know that Fourier transforms, this is all Fourier scales. So we're picking up the smallest Fourier scales. And in order to get back to an actual image, we have to do a Fourier transform. Combined with that, each telescope only has a small field of view, and you need to point them all in the same direction. So really, if you're looking at the sky, it looks more like this. It's actually more of a round aperture. So you're seeing like this tiny piece, and you're only picking up certain angular scales. So in an individual observation, you'll get this little tiny piece on the sky with just a sampling of angular scales, and basically my job is to Fourier transform all of those and then build them up into one giant image. Now that normally takes thousands of observations. You can get a larger field of view by making your telescope smaller, but then you've got less collecting area, so then you've got less sensitivity. So there's this trade-off. But generally it takes thousands of observations to look at the whole sky, and as I say, that's a big data storage problem. You've got a Blu-ray per observation. Doing all of these Fourier transforms is very expensive, and that's the main thing that our supercomputers are doing. And of course, all of this takes an enormous amount of storage. So we have to not only store all the raw data, but we process it and then store all those outputs. And so, of course, this is all done as a team effort. It's not just me, even though the picture is just of me. We have research groups. We employ all sorts of people from computer science to physics, and the physics can be, theoretical astrophysics, observational astrophysics, simulations. So there's lots of, it's not like every person does all of these things. You know, we work together in teams. So this is the kind of result that you get if you do this with a real image. So this is, as I said, look out for what the acronym means. This is GLEAM. And this is a project that I ran from about 2013 to 2018, looking at the entire sky with the Murchison Wide Field Array. And that was quite fun and quite a lot of effort. So in total, we captured about a petabyte of data, and it took about 2 million CPU hours. So like if you ran a single core computer, it would take you 2 million hours to process all of this. And what that has led to is this full sky image, which spans 72 to 231 megahertz, basically a very wide bandwidth of the electromagnetic spectrum. And you can see all sorts of fantastic astrophysics in here, which I don't have time to go into. But I will just say that this bar across the middle here is our own Milky Way galaxy, which we're inside. And this here is a radio galaxy, like I showed you earlier. And all of the thousands of dots are other radio galaxies, billions of light years away. And so we're able to explore like deep into the cosmos with these kinds of data. So if you want to know more, there's a talk here, bit.ly/NHW-TED. If you go there, you can see literally the TED talk. All right, so that's pretty much what we've been doing for the last 10 years or so. Before that, we didn't even need supercomputers. You could do the kind of radio astronomy calculations on your laptop. But nowadays we use supercomputers, and the problem is that in the future, the telescopes are, they're getting more capable, they're getting bigger, they're getting more sensitive, there's more elements. And so the kinds of data that we're producing are starting to get a little bit out of hand. So with our telescope and our survey, I've looked through enormous amounts of that, by eye, and I've run automated source finding. But it's still kind of not enough to actually extract all of the science out of the data. And with future telescopes, that's just going to get worse. So some of the techniques that we've been using, we do citizen science projects. So we say we want to classify radio galaxies into different kinds, or like look at their features. We might build a website where people can go and click and classify the galaxies, and then that can curate our data set for us. Of course, that requires lots of people and lots of buy-in, and that's still a lot of effort. That's a lot of humans. So what we're doing nowadays is we take those classifications and we train machine learning neural networks. And then we have an automated system that doesn't get bored, that can do all the classification for us, extract some science. Sometime later you get the TED talk. So this is a really new thing, and it's a real growth area in all fields of astronomy. And if you want to check out more, there's a link at the bottom to one of the most successful projects, Galaxy Zoo. Another aspect in which we use data during astronomy is in outreach. So this is something I'm very passionate about. I give a lot of public talks, but I also help build like apps and ways that people can kind of get into radio astronomy, from a public point of view. So this is showing the GLEAM VR app. If you have iOS, if you have Android, you can type GLEAM into the Play and Apple stores. I think I've got that the wrong way around, but Apple and Play stores. And you can get the view of the radio sky on your phone. And you can hear me and my colleagues talk a little bit about the different features. And it's really quite immersive to have this as a radio headset. So you can kind of look around and really see the sky. And also I've exported a lot of this data to planetariums across the world. So yeah, that's another way in which we use data. So if you're interested in finding out a bit more about astronomy and how you can apply physics and computing and mathematics, I would really recommend talking to us. We run summer programs for undergraduates so that you can literally, I'll give you data, you can go and find new radio galaxies or understand physics. It's a very cool program. We're just selecting students at the moment, so next year would be the time to apply for that. But I think the School of Computing, Engineering and Mathematics is going to be running a summer program as well. And I learned a lot from doing summer projects. That's where I got my love for research, so I'd highly recommend that. There's lots of free seminars, check them out. And yeah, come talk to us afterwards and compare your, what you want to do to what's out there. Now, I know I've reached my time, but I did just want to quickly show you some of this. So the reason that I'm even here, like 15 years ago, there weren't any radio astronomers in WA. Now there's hundreds of us. And the reason is because this wonderful site that we have up in the Murchison is going to be home to the Square Kilometre Array, or at least half of it anyway. And this is a test bed for the Square Kilometre Array, so you can see us actually building test equipment, which is all functional, and we're taking real images of the sky right now. And we're basically going to be building across tens of kilometers instead of our 5 kilometers, hundreds of thousands of antennas instead of our thousands. And this will give us more sensitivity, more resolution, more bandwidth. It's going to be amazing. And basically they're starting construction now. So hopefully, if you're interested in getting in astronomy now, in a few years' time you could be working with early data from the world's largest radio telescope, and all the computation will be done right here in Perth. So it's good timing. All right, thank you very much. Happy to take questions if we've got time.